Imagine two candles burning in a cathedral the size of a galaxy. Each flame is real. Each one is warm and bright and alive with chemistry and light. But the cathedral is so vast that neither flame can feel the other's heat, and neither can see the other's glow. And the distance between them is so enormous that even the fastest thing in the universe, light itself, would need tens of thousands of years to carry a message from one to the other. Now imagine that each candle burns for only a moment, a few thousand years, a few million if it is lucky, and that the cathedral has been here for 13 billion years, and that during all of that time, candles have been flickering on and off across its entire expanse, but never at the same time, never in the same place, never close enough to each other and overlapping enough in their brief burning to ever know the other was there. This is not a metaphor chosen for its melancholy. It is as close to an accurate physical description of the situation as ordinary language can provide. The universe is vast beyond imagining. The civilizations that may exist within it are separated not just by distance, but by time, by the specific geometry of an expanding cosmos, by the absolute ceiling of light speed, and by the fragility of intelligence itself. And when you sit with all of these things together, when you refuse to round the numbers or soften the physics, you arrive at one of the most quietly devastating conclusions in modern science. Two civilizations meeting each other face to face across the gulf of space is not merely unlikely. Yes, it may be the rarest event that the laws of physics permit to occur in any universe remotely like this one. The universe should be full of life. Let us begin there, because that is the honest starting point. The mathematics is not subtle. There are an estimated 200 to 400 billion stars in the Milky Way alone. Observations by space missions over the past few decades, particularly the Kepler Space Telescope, which monitored a small patch of sky and found planets around nearly every star it examined, have established that planets are not the exception. They are the rule. Most stars have them. Many have several. A substantial fraction have planets orbiting at distances where liquid water could exist on their surfaces. And liquid water, as far as we understand chemistry and biology, is the single most important ingredient for the kind of complexity that produces life. Multiply the number of potentially habitable planets in the Milky Way by the number of galaxies in the observable universe, roughly 2 trillion of them, and you arrive at a number so large it collapses all intuition. Not billions of possible worlds, not trillions, numbers that require scientific notation to write, numbers that exceed the total count of grains of sand on every beach on Earth by many orders of magnitude. If life arises on even a vanishingly small fraction of these worlds, 1 in a billion, 1 in a trillion, the universe should still be teeming with it. This is not speculation, it is arithmetic. The sheer scale of the cosmos makes the emergence of life somewhere else almost a certainty. Yet, in the same way that with a large enough shuffled deck of cards, any particular combination must eventually appear. The deck here is incomprehensibly large. The combination we are asking about, chemistry becoming biology, biology becoming complexity, complexity becoming something that looks up at the sky, has already occurred at least once. And yet, the sky is silent. The galaxy presents no confirmed evidence of another mind. No ship has appeared in our sky. No signal has arrived that we can unambiguously decode as the product of intelligence. SETI, the search for extraterrestrial intelligence, has been operating in various forms since the early 1960s, scanning the sky with radio telescopes and, more recently, optical instruments. 60 years of listening, and the silence has never broken. This is the Fermi paradox. In name for the Italian-American physicist Enrico Fermi, who in 1950 sat down to lunch at Los Alamos National Laboratory and reportedly asked, with the directness for which he was known, given the age and size of the universe, where is everybody? It is the simplest and most profound question in science. And the answer, when you follow the physics and the mathematics with care and without optimism as a guide, is not one answer, but a constellation of them, each one revealing a different wall the universe has built between any 2 points of light and mind. The first and most immediate wall is the one we have already glimpsed, distance, pure, astronomical, overwhelming distance. The nearest star to our sun is Proxima Centauri, a red dwarf star 4.24 light-years away. Light, moving at nearly 300,000 kilometers per second. It takes 4 years and roughly 3 months to make that crossing. A spacecraft traveling at the speed of our most advanced current probe, Voyager 1, which has been traveling for nearly 5 decades, would require approximately 73,000 years to cover the same distance. 73,000 years. That number deserves to be held, not moved past quickly. It is longer than all of recorded human history. It is longer than the oldest cave paintings. It is longer than the entire span of time during which modern humans have been using language. And that is the nearest star. A civilization located 1,000 light-years away, well within our own galaxy, well within what astronomers would call our cosmic neighborhood, would be separated from us by a distance that light takes a full millennium to cross. As the Milky Way itself is approximately 100,000 light-years across. A civilization on the far side of the galaxy, looking toward us, is separated by a gulf that light takes 100,000 years to traverse. The human brain cannot hold that number. It cannot hold what 100,000 years of travel actually means, what it would take to sustain any mission or any signal across that expanse, what changes between departure and arrival when the gap is wider than the entire span of human existence on Earth. And these are all intergalactic distances. The nearest large galaxy to the Milky Way, the Andromeda Galaxy, is approximately 2.5 million light-years away. The observable universe extends in all directions to a radius of about 46 billion light-years, a sphere encompassing 2 trillion galaxies. Each containing hundreds of billions of stars, each separated from the next by millions of light-years of essentially empty space. The universe is not just large, it is large in a specific way that directly undermines the possibility of contact. It is large enough that even if civilizations arose frequently, they would almost always arise too far apart from one another for any physical exchange to be possible. But distance alone, as staggering as it is, does not fully explain the silence. Because distance could theoretically be bridged with enough time and enough technology if both existed in the right combination. The deeper problem, the second wall, is that the universe has set an absolute speed limit on information and matter. And that limit is not fast enough to make meeting across these distances possible in any meaningful sense. The speed of light in vacuum is approximately 299,792 kilometers per second. Einstein's special theory of relativity, published in 1905 and confirmed by every experiment physics has performed since, establishes this not as the speed of light specifically, but as the speed of causality, the maximum speed at which any influence, any signal, any physical object with mass can travel through space. Nothing with mass can reach this speed. The energy required to accelerate any massive object to c is infinite, not very large, infinite. This means that any physical spacecraft, any object made of matter and carrying matter, is confined to speeds below c, significantly below it. But with any technology we can currently conceive, the best proposals in the physics literature, nuclear fusion drives, antimatter propulsion, laser-powered light sails, might, in their theoretical optimum form, achieve 10 to 20% of the speed of light. At 10% of c, the journey to Proxima Centauri takes 42 years. The journey across the Milky Way takes 1,000,000 years. The journey to Andromeda takes 25 million years. Even granting that relativistic time dilation, the genuine physical slowing of time for fast-moving objects predicted by relativity, would allow a crew to experience less time than the distance in light-years might suggest, the problem for any meeting between civilizations does not disappear. The travelers age at a compressed rate, but the universe around them does not. Yet the world they came from ages normally. The civilization that built their ship changes, evolves, collapses, rebuilds over the centuries or millennia that pass during a transit. And the destination, if it contains another civilization, has also changed, perhaps beyond recognition, perhaps beyond existence, in the time it took the travelers to arrive. This is the temporal dimension of the meeting problem, and it is perhaps the most overlooked wall of all. Consider what it would require for 2 civilizations to actually meet. Not just for one to send a probe that eventually drifts into another's territory after 1,000,000 years, carrying frozen information about a society long extinct, but for 2 living, active, communicating civilizations to be in genuine contact, to exchange ideas and culture and knowledge in something approaching a relationship rather than an archaeological excavation. This requires not just that the two civilizations exist, but that they exist at the same time, that their technological phases overlap, that the distance between them is small enough for a signal to travel during the relevant period, and that both are both willing and capable of making contact. Each of these requirements is a filter that the universe applies silently and without malice to every pair of civilizations in its history. And the product of all these filters together is a probability so small that it may, in practice, be essentially zero. Think about the temporal problem alone. Now, the Milky Way is approximately 13.6 billion years old. The first generation of stars formed within the first few 100 million years after the Big Bang, but those early stars were massive, short-lived, and composed almost entirely of hydrogen and helium. They produced none of the heavier elements that complex chemistry and biology require. Carbon, oxygen, nitrogen, phosphorus, iron, the elements that life as we know it depends on, were forged inside stars and distributed across space by supernova explosions, enriching the interstellar medium over billions of years. It was not until the galaxy was several billion years old that the metallicity of star-forming regions was high enough to reliably produce rocky planets with the chemical complexity needed for life. This means that life-bearing worlds, statistically, are a relatively recent phenomenon in galactic history. The Earth itself formed about 4.5 billion years ago. Complex animal life appeared only about 600 million years ago. Intelligence that can build technology is perhaps a few million years old in our case. And technological civilization, the kind that produces electromagnetic signals detectable from other star systems, is barely a century old, 1 century, out of 13.6 billion years. Our radio transmissions, the leakage of television and radar and satellite signals that constitutes our inadvertent announcement to the cosmos, have been spreading outward from Earth at the speed of light for roughly 100 years. They have currently reached a sphere of space roughly 100 light-years in radius. The Milky Way is 1,000 times wider than that. Our signal has barely left the neighborhood. An alien civilization 200 light-years away would not yet have received our first radio transmission. A civilization 1,000 light-years away would have no idea we exist. And conversely, if there is a civilization 1,000 light-years away that developed radio technology 1,000 years ago and then went extinct 500 years ago, their last signals are still 500 years away from reaching us. We will detect a ghost, the echo of a civilization that no longer exists by the time we hear it, and by the time we try to reply, another 1,000 years will have passed, and there will be nothing at the other end to receive our answer. This is the brief window problem. Discussed in the scientific literature with increasing seriousness. The window during which any given civilization produces detectable signals may be extraordinarily short on cosmic timescales, a few centuries, a few millennia, perhaps a few million years at most, for any civilization lucky enough to survive its own technological adolescence. And the windows of two civilizations must overlap not just in time, but in proximity, close enough that signals can make the round trip during the active period of both. The probability of this happening for any two randomly chosen civilizations in a galaxy 13 billion years old is vanishingly small, even if civilizations are common. Now, add the third wall. The wall that operates not on the scale of individual civilizations or even the galaxy, but on the scale of the universe itself. The wall that the cosmos has been building, quietly and unstoppably, since roughly 5 billion years ago. The universe is expanding, not in the sense of matter flying outward through pre-existing space, like fragments of an explosion, but in the deeper sense that space itself is growing. The fabric of space-time is stretching, and as it stretches, it carries the galaxies embedded in it away from one another. The farther apart two galaxies are, the faster the space between them grows. Not because either galaxy is accelerating through space, but because there is simply more space between them being created by the expansion, and the rate of that creation accumulates with distance. In 1998, about two independent teams of astronomers studying the light from distant supernova made a discovery so surprising it won the Nobel Prize 12 years later. The expansion of the universe is not slowing down, as gravity would suggest. It is accelerating. Something, Physicists call it dark energy, and it constitutes approximately 68% of the total energy content of the universe, is driving the expansion to go faster and faster over time. The nature of dark energy remains one of the deepest unsolved problems in physics. Recent data from instruments like the Dark Energy Spectroscopic Instrument and new theoretical frameworks have begun to challenge the simple cosmological constant model, suggesting dark energy may be evolving over time rather than remaining fixed. But whatever its precise nature, the acceleration of the universe's expansion is observationally confirmed. It is happening, and its consequences for the possibility of civilizations ever meeting are profound. Because of this accelerating expansion, there is a limit to how far away any object can be and still be reachable from here, even in principle, even given infinite time. This boundary is called the cosmic event horizon. Objects beyond it are receding from us faster than the speed of light, not because they are moving through space faster than light, but because the space between us and them is growing faster than light can traverse it. No signal we send today will ever reach them. No signal they send will ever reach us. They are beyond the edge of what is, for us, forever inaccessible. The cosmic event horizon is currently located at roughly 16 billion light-years from Earth. Objects beyond that distance are, in the most absolute physical sense, permanently beyond reach. And because dark energy is causing the expansion to accelerate, this horizon is not static. It is shrinking in terms of what fraction of the observable universe lies within it. Galaxies that are currently within our reach are being carried toward and then beyond the horizon as time passes. The physicist Dan Hooper, working at Fermi National Accelerator Laboratory, calculated that within approximately 100 billion years, all stars and galaxies that are not gravitationally bound to our local group will have crossed this horizon and become not just unobservable but causally disconnected, forever beyond any possible interaction, forever beyond any meeting. 100 billion years sounds like an eternity. On human timescales, it is. But the universe is already 13.8 billion years old, and stars will continue forming, and planetary systems will continue hosting potential life for trillions of years into the future. The vast majority of the universe's life-bearing era lies ahead of us, not behind. And throughout all of that time, the cosmic horizon will continue to shrink. The accessible universe will continue to contract, and the prison of space will gradually become more confining rather than less. In the very long run, the local group, our cluster of roughly 50 galaxies, gravitationally bound together and immune to the expansion of space, will eventually merge into a single large galaxy, sometimes called Milkometa. A fusion of the Milky Way and Andromeda expected to begin its collision in about 4.5 billion years. Everything outside the local group will, on timescales of tens to hundreds of billions of years, recede beyond the horizon forever. Future astronomers, if there are any, will live in a universe that appears to contain only one large galaxy. The evidence for the universe's true scale and structure will have been erased by the expansion. They will not know what we know. The cosmos will have hidden its own history. This is the fourth wall, and it is in some ways the most final. Cosmic expansion does not just make meeting difficult for civilizations in the present epoch. It makes the universe progressively more isolated over time as dark energy continues its patient and relentless work of separating everything from everything else. But let us return from the cosmological scale to the immediate one, because there is another layer of the meeting problem that operates not on billions of years, but on the scale of human experience and civilizational history. The wall of what meeting would actually require. Suppose, against all the odds we have been examining, two civilizations happen to be close enough to each other and active at overlapping times for signals to pass between them. What would the exchange look like? The nearest plausibly habitable world we know of, Proxima Centauri b, orbiting the red dwarf star just 4.24 light-years away, is separated from Earth by a light travel time of more than 4 years. A message sent today would arrive there in roughly 4 years. Now, any reply would take another 4 years to return. A conversation, a genuine back-and-forth exchange of ideas, would unfold at a pace of 8-year gaps between each exchange, not 8 seconds, not 8 days, 8 years. For a civilization 100 light-years away, each exchange takes 2 centuries. For a civilization 1,000 light-years away, 2 millennia per exchange. The concept of conversation breaks down entirely. What we would be doing is not communicating in any recognizable sense. We would be sending messages into a future we cannot predict, to a civilization we cannot know, that might receive our words in a world utterly transformed from the one in which we sent them. The archaeologist studying a clay tablet inscribed 3,000 years ago is engaged in something more immediate than a round-trip communication with a civilization 1,000 light years away. The tablet is here. Its creator is gone. But the gap is finite, the language is sometimes decipherable, and the artifacts are at hand. An interstellar communication is the tablet without the artifact, the language without the context, the message stretched across centuries of silence, answered by a reply that arrives when everyone who sent the original message is dead, and interpreted by people who share no culture or evolutionary history with the senders. This is not a failure of technology. And it is a structural feature of a universe in which the speed of communication is finite, and the distances are so vast that even at the maximum physically possible rate of information transfer, the time gaps between exchanges exceed the typical lifespan of civilizations and the attention spans of species. And yet, and here the story becomes not more hopeless but more interesting, the universe has not completely prevented civilizations from knowing each other exists. It has merely prevented them from meeting, from talking, from anything resembling a relationship in the way we understand relationships. What it has permitted is a form of knowing that is slower and stranger, and more one-directional than anything our social instincts were built to accommodate. Light carries information across space, the signatures of chemistry, of biology, and of technology, the specific wavelengths absorbed and emitted by different molecules, the patterns in atmospheric composition that life leaves behind, the artificial signals that technological civilizations leak into space, can, in principle, travel across hundreds or thousands of light years and be detected by sufficiently sensitive instruments. This is the logic of astrobiology and remote sensing. This is why the James Webb Space Telescope, launched in 2021 and now operating at a distance of 1.5 million kilometers from Earth, is being used to study the atmospheres of exoplanets for biosignatures, chemical combinations like oxygen, methane, and water vapor in specific ratios that, on Earth, are produced and maintained by living processes, not proof of intelligence, but the possibility of life, or written in the spectrum of light that a distant planet reflects. We cannot visit these worlds in any meaningful human time frame. We cannot send a greeting and wait for a reply. But we can potentially know they exist. And that knowing, that awareness of life across a distance that will never be physically bridged, that recognition of another flame burning in another part of the cathedral, is something. It is not nothing. It is perhaps all the universe intends to give us. There is a hypothesis in the scientific literature called the dark forest theory, named for a concept developed by the Chinese science fiction writer Liu Cixin in his trilogy of novels, but reflecting a real possibility that some researchers take seriously. In this framework, the silence of the universe is not the silence of emptiness, but the silence of deliberate concealment. Every civilization, the argument goes, knows two things: that resources are finite and that any other civilization encountered might eventually become a threat. In a universe where meeting is nearly impossible, but detection is conceivable, the safest strategy for any civilization is to hide, to go quiet, to emit no signals that could betray their location to a predator more advanced than themselves. This is an uncomfortable idea. It suggests that the silence we hear in the night sky may not be the silence of absence, but the silence of fear, a galaxy full of civilizations all choosing not to speak, all drawing the same conclusion about the danger of announcement, all burning their candles behind closed shutters in a cathedral where every other candle does the same. The physicist Stephen Webb, in his book on the Fermi paradox, cataloged 50 different proposed solutions. The dark forest is among them. So is the hypothesis that sufficiently advanced civilizations inevitably transition to a post-biological, possibly digital existence, and that such civilizations would have no recognizable motivation for physical exploration or expansion. So is the hypothesis that intelligence capable of interstellar communication is genuinely extraordinarily rare, rarer than we tend to assume, and that the silence reflects scarcity rather than concealment or destruction. And there is the possibility that we are simply early, that the universe is only now, in its present epoch, yet reaching the chemical and stellar conditions that favor the emergence of complex life in large numbers, that the galaxy is not full of ancient, silent civilizations that have come and gone, that we are among the first, or close to it, and the silence is the silence of a beginning rather than the silence of an ending. The astronomer and author Carl Sagan understood the Fermi paradox as fundamentally a question about civilizational longevity. He recognized that the key variable in any estimate of how many communicating civilizations exist is not how often life arises or even how often intelligence develops, but how long technological civilizations survive after they develop the capacity to destroy themselves. We have had nuclear weapons for fewer than 80 years. Yet we have had the capacity to alter our planet's climate for perhaps a century. These are capabilities that arrived very quickly, and the question of whether we will manage them wisely is not yet answered. Sagan believed, hoped, perhaps more than believed, that the resolution of this period, the navigation of what he called the technological adolescence of a civilization, was the key transition. That any civilization that managed to survive its own power, that found a way to endure past the era of self-extinction risk, would go on to persist for extraordinarily long periods, would become, over millions or billions of years, the kind of civilization that might be capable of making itself known across interstellar distances, if not of physically traveling them. But surviving that transition is not guaranteed. And the silence of the sky is consistent with a universe in which most civilizations do not survive it, in which the candles are real and have been burning intermittently throughout the galaxy's history, but have each burned briefly and gone dark before any signal they emitted could make the round trip to a neighbor and back. The brief window hypothesis formalizes this intuition. It suggests that the period during which any given civilization actively communicates across interstellar distances, the window during which its signals are strong enough to detect and it is both willing and able to broadcast and receive, may be very short on cosmic timescales, perhaps a few thousand years, perhaps a few million for particularly durable civilizations, and that for two civilizations to have overlapping windows, and to be close enough to each other that light can make the round trip during the overlap, and to be both listening and broadcasting at the right frequencies, the product of all these probabilities may be so small that in a galaxy of hundreds of billions of stars across 13 billion years of history, it has simply never happened, or has happened only rarely, in places and at times we cannot yet see. There is something in all of this that resists easy emotional resolution. The universe is vast. It is probably populated with life. And the fundamental geometry of space-time, the speed limit of light, the acceleration of cosmic expansion, the brevity of civilizational windows, and the enormous improbability of temporal and spatial overlap. These things conspire together to make genuine meeting essentially impossible for any two civilizations not in immediate cosmic proximity and not active at precisely overlapping times. The candles burn. They have always burned, but the cathedral is too large, and the flames too brief, and the space between them too great for any two flames to ever warm each other. And yet we are here, asking the question. We are the candle that has become aware of the cathedral, that has measured its dimensions and calculated the distances and understood, with a precision that no previous generation of minds possessed, exactly how vast and how empty and how fundamentally isolating the structure of the universe really is. That understanding is itself something extraordinary. Whilst it required billions of years of stellar evolution to produce the elements we are made of. It required the specific, improbable history of Earth to produce biology, and the specific, improbable history of biology to produce intelligence, and the specific, improbable history of intelligence to produce science. And science, in a few centuries of accelerating inquiry, has produced this view of the cosmos, this clear, cold, honest picture of a universe in which meeting is nearly impossible, and the silence of the sky is not a mystery to be solved but a structure to be understood. Knowing this does not make us smaller. It makes us more astonishing. The fact that a universe built the way this one is built, governed by the laws that govern it, expanding at the rate it expands, yes, enforcing the speed limits it enforces, the fact that such a universe produced anywhere, a mind capable of working all of this out, is among the most remarkable things that can be said about the cosmos. We may never meet another civilization. The physics suggests we probably will not. The distances are too great, the windows too brief, the speed limit too absolute, and the expansion of space too relentless for any two candles in this cathedral to do more than, at best, glimpse the faint light of each other across an unbridgeable darkness. But we have glimpsed the darkness and understood it. We have measured the cathedral and found it magnificent even in its emptiness. We have asked the question and followed it honestly into its most uncomfortable answers and found that those answers, for all their loneliness, yet carry a kind of beauty. The universe was not built for meetings, but it was apparently capable of producing something that knows this, something that looks out at the great silence and calls it by its name, something that burns briefly and brightly in the dark, knowing the dark is very large and burns anyway. Perhaps that is what candles have always done.